Can you please rise as we welcome the procession inside the venue? Thank you so much. Thank you. You may be seated. Prof. Fielding.
Good evening. Good evening. You mathematicians are very, very quiet. Colleagues, friends, students, welcome to a very important event tonight. We're here to celebrate a colleague of ours, a colleague that's nogal an A1 rated researcher. So for those of you in the field, you know that is a very unicorn type of person to see. So we're very proud to be here tonight and just to enjoy tonight. I've made some notes that I have to read. The accolades are just way too many to have memorized. Florian Luca is a professor of mathematics, that at least I know, at Stellenbosch University. Before joining in 2024, he was a distinguished research professor at WITS. He completed his PhD in mathematics from the University of Alaska Fairbanks in 1996. He's also been employed at Bielefeld University, Germany, the Czech Academy of Sciences, and the National Autonomous University of Mexico. So I did a Google search, and the Google search gave me incorrect information. It said he only has 500 publications. So I apologize, Florian. Apparently he has more than 800 publications. He has an H-index of 40. So if you don't know what that means, it means that at least 40 of his publications have been cited at least 40 times. Now, for a mathematician who works in a field that I do not understand, that is very, very impressive. It means that his work is not only impactful for society, but also in academia. More than 9,600 citations, and he's had a slow year thus far. He's only published 15 publications in 2025 thus far. So, Florian, we're a bit disappointed that it's only 15, and we're looking forward to the next 35 for the rest of the year. In recognition of his work, he has received various international awards. Let me just list some of them. He's an Alexander von Humboldt Fellow. Do you know what that means? It means that even though it was awarded in 1998, this is a league of fellows that belongs to a fellowship that meets very frequently globally. So he's covered for the rest of his life. Not just academic life, but for the rest of his life. So imagine the prestige that he brings to Stellenbosch. He's also been awarded a Guggenheim Fellowship in the United States, 2005. He's a CNRS Ambassador Fellow from France, and that was awarded in 2024. He is a member of the African Academy of Sciences, as well as the Academy of Science of South Africa. He's been A-rated twice by the National Research Foundation. And I have to confess, when I saw the title, I actually thought it was Lord of the Rings or something. So today, the entire day, I actually sat down and I tried to figure out, how do I say something about his work? Ended up with nothing. I then went to Google, to ChatGPT, and I asked ChatGPT, give me a summary of the work that he does. ChatGPT broke. So I still have no idea what he does, but I'm excited because we're listening to an A1 rated researcher that has global impact, who's considered a global leader. There's nothing higher than what Florian has achieved. So I am sure that you are all excited with me, and we're looking forward to the presentation. Florian, once again, from the faculty and from our colleagues and friends and our students in the audience. We look forward to tonight. Congratulations.
Thank you very much, Dean, for your kind words, and thank you all of you colleagues for coming here to listen to a talk about mathematics. It's not going to be exactly mathematics today. It's going to be a little bit of theoretical computer science, mathematics, and landscape. Let's see, what is the Skolem landscape? So I'm going to talk in terms of, shall I speak in the mic? Shall I? Oh, I see. So can I? Oh, I can use this one. Oh, wow, I feel like a rock star. 1, 2, 3, let's go. Okay, so the program termination. The question is, what is the simplest class of programs for which deciding termination is not obvious? And I'm just going to take you basically back to school. So simple linear loops. You've all seen that, no matter whether you're an engineer or a mathematician, or you might have gone into something like this, where you have some set of variables which are subject to some rules. For example, they might start with 1, 0, 0, and as long as one of them is not equal to 0, then change x, y, and z according to those rules. Make x to be equal to 2x plus y, and so on. So then there are two things that we can ask here. The general question is start with some set of variables that has a certain initialization. We'll call it A. And as long as the first component is not equal to 0, change that x according to some linear rule, m times x, where m is a matrix. Or we can say as long as the first component is greater or equal to 0, do this. So the question termination is, does this program ever terminate? What does it mean to terminate? Does it ever get to 0? Once that variable gets to 0, then you cannot continue. So the first problem, it's called the Skolem problem. So this is what we will be talking about. The second problem, it's called the positivity problem. The positivity problem is harder than the Skolem problem. So today we'll report about things that are known about the Skolem problem. So what exactly are the Skolem and the positivity problems? You take a square matrix, k by k, think of an array of numbers, 3 by 3, and then is there a positive integer n such that if you start with, let's say, 3 values and you apply this matrix, then at some point the top right entry of this matrix, let's say m to the power n, it's equal to 0. And the positivity is the question, is it the case that for all positive integers n, the top right entry of m to the power n is greater or equal to 0? And you would see how this would have, let's say, applications. If you work on some engine or something, maybe x equal to 0 means something breaks down or some plane falls on water. Or so you want to be able to predict whether something like this will happen or not. So this leads us to something called linearly recurrent sequences. What is a linearly recurrent sequence? A sequence is just a set of numbers given in some order. So you have the first term and the second term and the third term and so on. And then it's linearly recurrent if each one of these terms can be obtained in some linear way by summing up, let's say, a few of the previous terms with some fixed coefficient. And this is called a linearly recurrent sequence. For example, there are the Fibonacci numbers, which we are going to see them. What is the Fibonacci numbers? The Fibonacci numbers, they start with 1 and 1, the first 2 terms, and then every new term is obtained by summing up the previous 2. So let's see if you're paying attention. The next term is 1 plus 1 is 2. The next term is 1 plus 2 is 3. What is the next term? 5. Is 2 plus 3 is equal to 5. Very good. So the number k, it's called the order of the recurrence. So how many guys do you have to sum up in order to build the next guy? So Fibonacci has order 2. So the Skolem problem can be reformulated by saying, take a linearly recurrent sequence. Is there an n such that the nth term is equal to 0? And the positivity problem says, is it the case that u sub n is greater or equal to 0 for all n? And you're living in a finite world. You only have finitely many steps to decide. You can't go all the way to infinity. You have to cook up some procedure so that after you do things, let's say the first 1,000, 10,000, 1,000,000 times, you draw some conclusion and say, okay, from now on everything is going to be positive, or from now on there's not going to be a zero. So this is the problem that we are interested in. And here is what some very clever people have to say about it. This guy, Terence Tao, he's the Fields medalist. He's a professor at UCLA. He participated at various mathematical Olympiads when he was a child. He was taking big prizes even at the ages of 12 and 13 and 14. I think at 16 he stopped going because it was too easy for him. So he says that it is faintly outrageous that this problem is still open. That is, we do not know how to decide the halting problem even for linear automata. And then Richard Lipton, he's a theoretical computer scientist at Georgia Tech, calls it a mathematical embarrassment. Arguable by some distance, the most prominent problem whose decidability status is currently unknown. So what is known? What is known is that the set of zeros, so if you have an animal like this, a linearly recurrent sequence, then the set of zeros, they come in two ways. They are predictable ones and unpredictable ones. The predictable ones are easy to classify. They are called arithmetic progressions. I can give you an example of a linear recurrent sequence. 1, 0, 1, 0, 1, 0. Why is that the linear recurring sequence? Because every second term coincides with the previous term. So you can write the relation. U sub n plus 2 is equal to un. And then you start with 0 and 1, and then it will keep on going, 0 and 1, 0 and 1. So you understand those zeros. Those zeros are called somehow degenerate. But then there is a set of finitely many zeros, theoretically finitely many of them. It's known that they are only finitely many, but the proof is not effective. And this is what is important. There are quantitative statements about how many of them can there be. So if the sequence has order k, that is, you need k guys, let's say you need 100 guys in order to build up each successive term, then the sequence has at most the exponential of 70 to the power k. That is a very big number. And the reason that there's these people involved is that, for example, Schmidt, he had a tower of 3 exponentials. He had the exponential of the exponential of the exponential of 3k log k. And this one of 2011, it's by 1 exponential less. Probably the truth is that it's probably at most exponential in k. It's known that it could be at least k square or more, but so there are lower bounds, but we are interested in upper bounds. So when we talk degenerate and non-degenerate, a degenerate one is it can be written as some sort of a merge of lower ones, like the example I gave you with 0, 1, 0, 1. Somehow it's not it's a degenerate one. You start, let's say, with 2 constant sequences, 0 and 1, and then you kind of interlace them, but that is not so interesting. The non-constant ones, in general, they become big. So Skolem and positivity, they arise in many areas. You can even think about models in your head. For example, theoretical biology. Suppose that you're modeling some population of animals or something like that. And then what does 0 mean? It means extinction. So it is important to know whether that population, let's say, will disappear or no. Software verification, dynamical systems, differential privacy, and many other things that you can see written down there. So, practic. Does this program ever halt? Well, here's one trick. Since there are integers in there, we can do something to them that's called modulo. What does it mean, modulo? You take some number, you divide your number by that number, and you keep the remainder. So, for example, let's look at it modulo 3. So whenever you see a 3, then it becomes 0. So let's look at it modulo 3. What does x do? It starts 1, 0, 0. Then it gets here, x becomes, this one was 1, 2 times 1, it becomes a 2, and that's a 0, right? So the 1 here became 2. This guy that was 0 becomes 0, because that guy was 0. 3 modulo 3 is 0, so that also disappears. z was 0, so y stays constant 0. What does z do? Also stays constant 0, because this was minus 4 times 0 plus 6, but 6 disappears modulo 3. So after the first step, 1, 0, 0 went to 2, 0, 0. And then if you do it again, it goes back to 1, 0, 0. X will never become 0. So x is always a number which, when you divide it by 3, gives the remainder 1 or 2, so it cannot be the 0 number. Well, about the Fibonacci sequence, you probably know the story how the Fibonacci sequence appeared. The Fibonacci sequence appeared in a book written by Fibonacci, which is called Leapfrogging in 1200s. And this book was a collection of riddles that were used by various merchants. For example, if somebody would have so many cows and he wanted to change by so many goats and so on, you had to make a plan and figure out how, sort of what we do nowadays, you would teach your children to word problems in elementary school. So that was a collection, and this is where the Fibonacci sequence appears. So this is the rule. The rule is that you start with a pair of rabbits in the field, and the pair of rabbits mates after 1 month, but then it starts producing babies after the 2nd month. And then the question is, how many pairs are there after n months? So the month number 1 is there, they mated, but this is month number 2, it's still there. After month number 3, that's already another pair there, so that's 2. In month number 4, it's this corner, it's 4, and this is 3, and this is the rule. Now, if you try to play this rule, and you say, well, let me reduce it, modulo something, you notice that, for example, every 3rd guy, it's even. For example, this guy is even, this guy, the 6th guy is even, and then the 34th guy is even, and then the 144th guy is even. So every step of 3, you get an even number. Now, every step of 4, you get a number that's a multiple of 3. So this guy is a multiple of 3. Then you go 4 more, you get this guy, which is a multiple of 3. You go 4 more, you get this guy, which is a multiple of 3. So modulo every number, you're going to get zeros. And the question is, why is it that you're always going to get zeros? The trick is that there is a natural 0 that's embedded in there, which I didn't show you what it was. Instead of starting with 1, 1 and summing them up, you should put a 0 in the past there. If you put a 0 there, then that 0 plus this 1, it gives 1. Meaning that if you start with 0 in the position 0, then that 0 will kind of survive by reduction, modulo, reducing it, dividing it into various numbers and so on. So this 0 is always there. This is because the Fibonacci sequence is reversible, so you can go with it in the past. You are allowed to go with it in the past as long as you respect the rule. So the sum of every 2 of these numbers, they should give you the next number. So 2 plus minus 1 is 1, minus 1 plus 1 is 0, 1 plus 0 is 1, and so on. And this extension, which is by infinite, because now I can go to infinity in the future and I can go to infinity in the past, is periodic, modulo every m. So this is a classical Fibonacci sequence that I can go in the past with. I can have this arithmetical progression, all the integers, I can go in the past with that one. How about this one? Can I go in the past with this one? With this one, well, I can, but I have to stretch it. I have to accept guys like a half and a fourth and an eighth. Because the rule is that every number should be twice times the preceding number. So if I want to go a lot in that direction, then I have to allow fractions that have large powers of 2 in the denominator. So these guys are called z-reversible. These guys are called not z-reversible. So the Skolem problem is, now, suppose now that you take this sequence and you go with it in the past. You can do that with any linearly recurrent sequence. And then you ask, is there an integer such that u sub n is equal to 0? Maybe it's not in the future, maybe it's in the past. But if it was in the past, somehow it's going to be reflected in the future. Now, there are some things there which are called, for example, the sequence might be called simple or non-simple. It has something that I'm not going to get into technical details. To all these sequences, you can assign some polynomial, which is an equation, and that equation might have double roots or multiple roots. Then in that case, the roots are not simple. But in the case of the Fibonacci sequence, the roots are simple, and it looks like this. It's the only radical that you will see in this talk. The vast majority of the linearly recurrent sequences are simple. Because if you take a random polynomial, then with a huge probability, not only that it's not going to have a double root, but it's going to be reducible and so on. And if you think in terms of matrices, like I started, this corresponds to diagonalizable matrices. Well, let's see what the state of the art is. The state of the art is, if you go to sequences of order at most 4, the problem is decidable. For very low order, like order 1 or order 2, it's very easy. But for order 3 or 4, the classical ingredient is a theorem of Alan Baker. Alan Baker was a British mathematician. He was awarded the Fields Medal in 1970. He passed on about 10 years ago. So there is some very deep mathematics that goes inside there. The corollary is that the Skolem is decidable for sequences of order at most 4. Here is a little contribution. If you restrict z-reversible linearly recurrent sequences, for which you can go in the past without dividing into numbers, then order 7 is decidable, up to 7. And here is something that, for example, the first bad case scenario. The first bad case scenario is this kind of recurrence, which is of order 5. This one has what's called dominant roots, which are 4 of them. There are some complex numbers. They sit on the same circle. And then there's a smaller one in there, which is at 1. And empirically, it seems that for every n, for every k, there exists for every initial values, there exists a k, such that if you try to reduce this one modulo 5 to the power k, so you divide it into 5 to the power k and you look at what's left, it seems that this is equal to 0 only for finitely many n. So somehow this 5 to the power k should be a sort of a witness or a detector of whether there are zeros in this kind of sequence or not. So as we know about mathematics, in mathematics, what is mathematics? It's a game. You have some axioms and then you build between them and you deduce things which are called theorems. The important things are theorems. The non-important things may be called lemmas or propositions or whatever. However, there is no reason why you shouldn't take something which you take something which you assume to be true, you don't know that it holds or not, and you put it in there, almost like an axiom. And then, of course, if you get a contradiction along the way, it means that that thing was false that you put in there. But if you don't get a contradiction, maybe you can work with it. And for example, what we do, one of the classical things is to throw in some famous conjectures in mathematics, like the Riemann hypothesis or the hunch that factoring is difficult and it takes a long time and so on. And then you can build in them and you can get new results. For example, you can get a polynomial prime test for primalities testing, assuming this hypothesis, and you get the security of what your banking is doing. We don't know that it's secure. They all tell you that it is, but nobody knows that it is. And this is the RSA, which is called from the name of its inventors, Rivers, Shamir, and Adelman. And also there's something called the Shanwell's conjecture. So there is something called decidability of first-order theory of real arithmetic, where you throw in the exponential function. And here is the Shanwell's conjecture. So what it says, let's look at the second part. The first part is maybe complicated. Suppose that somebody throws you in numbers, and then you take those numbers and you take the exponentials of those numbers. And now you have gotten twice as many numbers. And then you can ask whether there are algebraic relations between those numbers. Well, the conjecture says that at least n of them will be algebraically independent. So for example, if n is equal to 1, and you start with the number 1, you have the number 1 and the number e, then this would say that one of them is a transcendental number, and it's known that e is a transcendental number, so it works for n is equal to 1 and alpha 1 is equal to 1. So what it means to be algebraically independent, it means that there are no trivial algebraic relations between them. You can't, let's say, add the squares of 2 of the guys and it's equal to twice the product of 3 others or something like that. So here are some examples. E is transcendental, pi is transcendental. What about e plus pi and e pi? Well, nobody knows. But certainly not both of them can be algebraic, because if both of them are algebraic, then each one of them is algebraic, and that's wrong. So at least one of them is transcendental. Incidentally, not put in the slide is the fact that e to the power pi is transcendental, which is very strange that we know that. We don't know that pi to the power e is transcendental, but we know that e to the power pi is transcendental. But that, as I said, that is an accident. That is a consequence of the fact that e to the power pi, if you further exponentiate it to little e, which is square root of -1, you get -1. Because of this relation, e to the power pi is transcendental. Okay, so what about e plus pi? You can apply that Schanuel's conjecture with alpha 1 equal 1, alpha 2 equal I times pi, and you get these 4 numbers. But this number is equal to -1, so that's an integer, and there should be at least 2 numbers which are algebraically independent in there, and this makes e and pi algebraically independent. So both e plus pi and e times pi should be transcendental, and that is an application of this conjecture. So in particular, all these numbers have to be rational. So in other way, if you want to say, well, whatever algebraic relation holds between them, it's there because somehow the algebraic relation is a tautology. As you say, x squared minus y squared is x minus y times x plus y, and I can put x equal e and y equal pi, but this doesn't mean that this says something about e and pi. This is something about the relation as being a trivial relation. Well, let's go back and reverse again the linear recurrences modulo m. By the way, I don't have a timer, so I'm wondering how much do I still have? Maybe another 20 minutes or so? Okay. So let's go and reverse them as we saw before. You can reverse them formally. Oops. Let's see, where is it? I can single out this guy and throw everything in the other side, and then I say, this guy u sub n is whatever it's in the other side divided by a sub k. So now I can look at it modulo m, but of course when you divide things, it's a little bit like they teach you in school. You should never divide by 0. So that's something that happens there. If this number, let's say a sub k is odd, then somehow it makes sense to reduce it modulo 2 because you're not dividing it by 0, but otherwise it's not. So we may require that a sub k and the modulus m are co-prime. So here is what we do. Let's look at this example which was not reversible, because here I have a half and a fourth and an 8. But I can look at it modulo 3. What does it even mean, a half? Modulo 3. Well, what does a half mean? Let's try to make a sense of a half. What does a half do? A half is the number that multiplied by 2 gives you 1. Well, let's think what modulo 3 believes. Modulo 3 says, oh, okay, so I have to find a number which if I multiply it by 2, it gives me a remainder 1 by division with 3. Well, how about 2 itself? 2 times 2 is 4, and that gives the remainder 1 by division by 3. So maybe a half is the same as 2. And because of the same reason, maybe a fourth is the same as 1. Because if I multiply a fourth by 4, I get the number 1, but 4 modulo 3 is 1. So let's see if that's correct. And you can see that modulo 3 believes that this sequence is an integer. It doesn't see anything wrong with it. Only if we think about the integers, then we see that there's something wrong with it. So here is slowly I'm approaching something called the Skolem conjecture. What does Skolem conjecture appear? It appeared formally in a paper published in 1937. So what Skolem believed, Skolem conjecture applies to simple, by infinite, linearly recurrent sequences. So what does simple mean? Because what the Skolem conjecture says, the Skolem conjecture says that if a sequence has a 0, then that sequence should be witnessed by some modulus. In one way, it is easy to see. If there is some modulus so that that sequence is never 0, like the example that I started with, which is 1, 2, 1, 2, 1, 2 modulo 3, then it's fine. If I find some modulus so that that sequence is never 0, then that sequence couldn't have been 0 as an integer, because otherwise reduced modulo that modulus, it would give me the 0. The important thing is the reverse one. The reverse one, what Skolem believes, and other people believe it too, Skolem believes that if the sequence has no 0, then there should be a witness. There should be a modulus that catches that. But it should be applying only to this one. For example, this one doesn't work. Why doesn't this one work? Because this one I can make it divisible by any number. How do I make it divisible, let's say, by 12? Well, it's easy. Make 2n plus 1 divisible by 3. What's a good n like that? Let's say n equal to 7. 2 times 7 plus 1 is 15. That's a multiple of 3. So this 3 sits inside here. And since n is 7, this is 2 to the 7, which is a multiple of 2 square. So I found it. I found a multiple of 12 that looks like this. So you can see you can separate the powers of 2 and you can separate the odd part. However, this one is not going to have an integer. It's going to have, well, it's not going to have a 0. It's going to have n equal minus 1/2 to be a 0. But how do you put n equal minus 1/2 in a linearly recurrent sequence? We don't know how to put rational numbers in there. And by infinite, as I said, it's because you can have some zeros for a while, and then you kind of omit them, and you shift your sequence, and you look only at the future. And in the future doesn't have any, but it did have some in the past, and those ones should be noticeable, modulo some modulus. So this is the actual conjecture. Consider this recurrence. Suppose that it is simple, then this sequence has no zeros if and only if there is some modulus that sees that it has non-zeros. And this is called witness. So this is witnessed modulo the sequence has no 0, then this will necessarily be witnessed. Now, the Skolem problem, if you believe the Skolem conjecture, you can solve the Skolem problem. Here is how a computer scientist would think. I'm a mathematician and I was surprised by that. What a computer scientist would do, a computer scientist, he runs 2 programs. He runs a program looking for the zeros of that sequence. And he runs another program looking for moduluses such that the nth term is never multiple of that. If that conjecture is true, one of the 2 programs will terminate. We don't care how long it takes. It will terminate. It will either find a 0 or it will find a witness that says that there's no 0. But you have to believe this conjecture in order for that to be true. So a little under the Skolem conjecture a couple years ago, we proved with this team that the Skolem problem for linear recurrent sequence of order 5 is decidable, assuming the Skolem conjecture, like that nasty example that I showed you, modulo 5 to the k. And then we found an algorithm which takes an input, a simple non-degenerate linear recurrent sequence, and produces its finite set of zeros. So in some sense, we solved it. However, we solved it under 2 things. We solved it under the Skolem conjecture and under the Piadik-Shanuel conjecture. Honestly, we believe we solved it because we don't know how to create a counterexample. The point is that this algorithm, it's implemented. You go there, you give it a sequence, it will end. It will give you a certificate meaning these are the only zeros because of this reason, and you can check them. There's no other zeros. However, we don't have a proof that it terminates except under these 2 conjectures. So the algorithm produces an independent conjecture-free correctness certificate, and it's implemented in an online tool called Skolem, which is hosted on the webpage of my colleague, Joël Waknin, at MPI, at the Max Planck Institute for Software Systems in Saarbrücken. So when you go there, and I hope you have sequences for which you are interested if you want to find zeros, because if you do, you should go to this webpage. This webpage, what you do, you give them 2 sets of numbers. The sets should have the same length. The first k guys are the coefficients of the minimal of the recurrence. The next guys are the initial terms. You have to promise that the sequence is simple and non-degenerate. So the program is not going to check that for you. The program is going to assume it. And then it's going to run, and it's going to produce this. For example, it's going to say, oh, the zeros of this guy are only 0, 1, and 4. And here is why. So what it's going to give you? It's going to give you a list of numbers with the property that if n is not 0, 1, or 4, then the nth term is non-zero modulo one of the numbers in this list that it's going to give you. This is why I'm saying that it's corrected. You can check that it is correct. So the technical tool is something called periodic leapfrogging. So I already explained to you why if the Skolem conjecture is true, then we can detect if it has a 0. But then the question is, how do you detect other zeros? Maybe it has more than 1. How can we find the other ones? Well, let's suppose that it has 1. You shift it to the origin. Then, assuming some other conjecture, which is the Piadik-Shanuel conjecture, I'm going to tell you what that is, then one can compute an integer such that if you go towards infinity by multiples of that integer, you're never going to hit 0. Maybe that integer is, let's say, 1,000. So you start with U0 equals 0, then you have 1,000, you have 2,000, you have 3,000, you have 4,000. None of them is equal to 0. So then what did you learn from this? Then you say, oh, okay. Then what I have to do now, I have to take my sequence, I split it into 1,000 subsequences, depending on the remaining of a division of the index by 1,000. In the multiples of 1,000, I already know that there's no 0. So now I have to look at the numbers which are multiples of 1,000 plus 1, or multiple of 1,000 plus 2. That's 1,000 different sequences. Each one of them is different. And then I go and I apply this again to it. Either there is no 0, and I find it because the Skolem conjecture is true. I find a modulus. Or there is a 0. If there is a 0, then I do this. And I say, hey, are you going to end? Yes, I'm going to end because I have that result that says that after x_f 70k time, I have exhausted all the zeros that they were possibly there. So this is a finite time algorithm. I'm not saying that it's going to terminate during our lifetime if the sequence is too bad, but so what is the Shanuel conjecture? I'm going to flash some things from transcendence theory at you. So suppose that you have some algebraic numbers. If these logarithms of them are linearly independent over the rationals, then they are linearly independent over the algebraic numbers. The Q version of that, so without p-adic things, was one of Hilbert's problem. Hilbert believed that if the logarithms of some algebraic numbers are linearly independent over Q, then they are linearly independent over Q bar. And this is what it was proved by Baker, and it got him his Fields Medal and so on. And Brumer basically took this and showed that it holds in a p-adic setting. And there is a conjecture that under the hypothesis of Brumer's theorem, then these logs are algebraically independent, are not only linearly independent over Q bar. And this is subject to the Shanuel conjecture. And there's a theorem of McIntyre and Wilke that the first order theory is decidable subject to Shanuel's conjecture. So if you combine those things, if you throw away the complicated language and what that means, it means that we can put them in our little machine and we can get results about zeros of these linearly recurrent sequences. And here is some program in action. It detects some zero, then it starts jumping around them. And then it jumps more and more and more. So we basically just took one of these codes and we saw what it does. All right. So now in the last 10 minutes? 3 minutes. Oh, okay. What about non-simple sequences? Okay. What about the non-simple sequences? And then we can ask for subsets of the Skolem problem. Can one solve the Skolem problem on interesting subsets, on the primes or something? So this is something that we invented, a universal Skolem set. What is a universal Skolem set? Now you change things. You don't say, oh, sequences with certain property, we can solve Skolem problem. How about we just throw away some of the integers? Maybe it's the integers who are bad. Let's throw away some of them, keep the rest. And maybe we can solve the Skolem problem on the rest. So let's call a set to be a universal Skolem set. If it's a subset of the integers, and there's an effective procedure that you throw a linear recurrence in there, and it gives you the set of zeros, but only on that subset. Let's say a universal halping time. Is the set of primes a universal Skolem set? Is the set of natural numbers a universal Skolem set? Is there a universal Skolem set of density 1? And here is the first universal Skolem set. What's important, it's not the fact that it's so technical, it's basically it has some formula. You start with some number, let's say the number 1. You take a function f which grows slowly, like the square root of the log. And then to each term of it, basically you take s of this very small value of it and you slap it with n factorial on top. So it's a sequence that grows like crazy. It starts with very small numbers and it grows really quickly. And we proved that whatever sequence you throw in there, you can solve the Skolem problem in that. We sent that to a conference in computer science. This just uses analytic number theory, and it got a distinguished paper award. Here's our paper. It only has 6 pages. And how thick is the set? The set is not thick. It's very thin. It grows like the factorials, but the factorials grow very slowly. So can we do better? And I went on the internet and I found a meme producer. It says, yes, we can. Well, how better can we do it? Well, we can find a universal Skolem set of density 1, well, of positive density. But this is a bit technical. You take a representation of a number where you try to write it as a large prime times another number plus another number. Let's say you have two parameters, Q and A, where Q and A are small and P is big, but P has to be a prime. And then the theorem is, again with some people, and this is James Maynard, who took the Fields Medal 4 years ago, a few years back. So take the numbers with the property that the number of representation of this number is at least as big as the fourth iterate of the logarithm of n. You take log of log of log of log of n. You know what are the last words of a drowning analytic number theory? Log, 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 log. So you take these numbers that satisfy this inequality, then S is a universal Skolem set, it has positive lower density, and it has density 1 subject to the Bateman-Horn conjecture. And what is the Bateman-Horn conjecture? It's a conjecture of these two guys. This is Paul Bateman and this is Roger Horn, which basically what they do is a little bit like twin primes, which have become very famous lately because of advances on short gaps between, small gaps between primes and so on, which says that if you take a pair of linear forms which don't vanish modulo any prime, like n and n plus 2, then not only that you find infinitely many primes, n such that both n and n plus 2 are primes, but you find some expected proportion of them, and the constant is the expected one, and that's the summary, and these are my co-authors, and Kosi, Danki, thank you. Oh, questions?
Okay, are there any questions? Yeah. I think there is a question. There was a question from, Sura.
Okay, go ahead.
Professor Sura?
Thank you for the honor. What's the next step after the universal Skolem set?
We don't
Conceptually,
know.
because
Well, conceptually, we have actually, after this, we have a very clean bound, which I say the largest zero of a linear recurrent sequence, which is non-degenerate, is smaller than some function. We have the function, we can write it explicitly in terms of, let's say, k, which is the length of the recurrence, and how complex it is, how big the coefficients are. Let's call it height, the maximum between the a's and the u's at the beginning. However, our conjecture is based on some sort of a Kramer-style argument. So our approach has something to do with primes. You try to reduce it modulo primes, except that somehow the primes don't work very well. They work up to a certain level, and after that they don't work. But then we can prove that the primes that don't work in a universal way, because somehow you reduce some small sequence in some point modulo this prime, and it becomes 0 without having been 0 or something. Those primes are very few. They are much fewer than the primes themselves, than let's say x over log x. They are very few primes. So now let's take those primes and throw them away and make a conjecture like Kramer's conjecture. Kramer's conjecture predicts that the distance between two primes is about log of x squared if you sit at x. Now let's suppose that Kramer's conjecture is true with good primes that don't come from these bad Skolem primes. Then our bound is true. So there's some connection between how things look like modulo p and the zeros of these linearly recurrent sequences, which has not been noticed before, and it's not even clear why would the primes have something to say about it. So that's one direction in which we are going, and see how far we can go there.
Thank you.
Any other questions? Okay, there's one. We can take.
Oh, Herbert.
Just say your name and then the question.
Thank you. My name is Herbert. How does this Skolem conjecture relate to sequences with non-constant coefficients?
There is a little bit of work done on that, where you have sequences which are not linearly recurrent, but for which the coefficients depend on the index n in a polynomial way. Those ones, there is something called the generating function of them. If you take the generating function of linear recurrent sequences, it's a rational function. It's a ratio of two polynomials. If you take the generating function of these other more complicated ones, these ones are not rational functions, but are functions that satisfy differential equation with constant coefficients. So those ones would be the next step, but there things are very vague. Like, it's difficult even to predict the sizes of them and the zeros, and it's not very much is known. Much more is known for the linear recurrent sequences.
So thank you very much. I think, so can we give a thank you again to Professor Florian Luca's lecture. Thank you so much for the presentation. So I just want to acknowledge, of course, to thank Professor Florian Luca for the lecture on the Skolem landscape. So from today, I think you know that everything that is good has to come to an end, and then under certain conditions. So at least, I think for the layman, maybe that's the easiest way to describe this. So I just want to say that, so this lecture, as you could see, has brought to life the beauty and relevance of mathematics, both in its classical roots and modern applications. So his talk, of course, has focused on a long-standing question in mathematics about predicting when certain patterns, which we call in this case sequences, for those of you who are probably not in maths, contain a zero. And while this problem, of course, has puzzled many mathematicians, like you saw from the remarks that were made from the presentation for almost a century, Professor Luca has developed, of course, in the work that is done, new methods that can be used to solve it, offering clear evidence when a solution is complete, of course. Even more fascinating is in his introduction of universal Skolem sets, special sets of numbers that help make this question easier to answer in certain cases. We have seen, I think, the examples that he has used that help to define the problem. So these ideas, of course, are not just theoretical. They have real potential for applications in areas like computing, and you have seen the examples that he has given, systems analysis, and also logic. And also, I think you can also apply to other fields when you think about it. So maybe in your own field, you can think about how is this applicable to my field? But maybe if you think about what conditions do I know when something ends or when it does not? And how do you feel when you punch in something and the computer is just going in circles, your algorithm is just going in circles and doesn't know when to stop? So you can think about it in other ways as well. So as a university, we are really honored to host Professor Luca, who's an international scholar, as you know. He's NRFA rated, which just means also he's recognized internationally. He joined us from Wits University, and I think our colleagues who are watching online, and also some colleagues at Wits who are probably watching online, we are so glad that he's here, but we also, of course, collaborate with all our friendly universities. And I also want to just say that, of course, it has been mentioned already in terms of his Google Scholar profile with an index of 40 and also over 9,607 citations to his work, which just show his standing. And I think for the students, we have a number of students who have joined us here, and we have also two colleagues who have joined us, and I should acknowledge them, Professor Martins from the UK, who's an astrophysicist. Professor Martins, can you raise your hand over there? Yes, and then Professor, there's also Dr. Andronicus, who's also an astrophysicist who has joined us also in the group. And then we also have the director for the National Institute for Theoretical and Computational Sciences, Professor Francesco. You also raise your hand, yeah, so that people see you. So I think what's important is that we have students amongst us, and I think, if you think about the role of the mathematical sciences, and also at this age where there's a lot of data that we deal with a lot of need for algorithms, it's just to really encourage you, to have a passion for mathematics if you don't already have one, but to fall in love with the maths and to think about, how you can apply it in the different fields that you have. So I just want to end by saying, so the maths, so the presentation today, of course, on the Skolem problem, again, as I mentioned, can be applied, of course, in the theoretical computational sciences, in control theory and dynamical systems, in number theory, and of course, algebraic geometry as well. So having said that, I just want to end by, before I congratulate Professor Florian, is also to acknowledge, the role that the faculty plays in making sure that we have an enabling environment for the students and also for the staff that we host at the university. So to acknowledge Professor Sam Tesla, who's the acting DVC Strategy, Global and Corporate Affairs, part of the panel, but also an applied mathematician. And I think you've appreciated the talk today as well. And then Professor Betty Fielding, the Dean of the Faculty of Science. And then we've got also Professor Ingrid Rewitsky, the Vice Dean Teaching and Learning. And then we've got also Professor Friki Scott, who's the Vice Dean Research at Postgraduate Studies and Internationalization, who's also on sabbatical. But thank you for coming for this lecture. At least it got you out of the sabbatical, so really great to have you here. And then Professor Gareth Boxer, who's the Division Head for Mathematics. And of course, our speaker, whom we really thank again for your talk. And I think you tried to break it down for us to understand. So I hope that our interpretation of the lecture shows the level at which you were able to break it down. So congratulations and well done for presenting this. The university obviously values these lecture sessions as they show the passage of the professor from in the academy to full professorship, and also acknowledge the work that he has done over decades and the training of students, which he has been very passionate about. And we look forward also to attracting more students also to the university in this field and contributing to the next generation of scholars. So congratulations and thank you very much.
Thank you very much.
Thank you. Can I ask, Prof, can you come to do the vote of thanks?
Right, so just a few words of thanks from the perspective of the mathematics division. First to Florian. It's been wonderful to have you in the division the past year. We've heard from Professor Fielding and Professor Moyer what a powerhouse of research Florian is, but he's not just a theorem-generating machine. He's been involved with our honours students, supervising, involved with seminars, bringing people to our number theory conference. So you've had a really big impact on the environment, and thank you very much for that. Thank you to Professor Moyer, Professor Chechler, Professor Fielding, Professor Ritsky, and Professor Scholz for supporting this event. And when I asked Florian who I should thank, he particularly expressed his appreciation for the support he's been given at Stellenbosch. So as representatives of management, thank you very much for your support of our superstar researcher and the mathematics division. Thank you to all of you for coming in person and online. It's great to see a lot of colleagues from mathematics and mathematical sciences more generally, and also a lot of students. And to non-mathematicians, maths is notoriously not a spectator sport, but I think Florian made it entertaining and accessible, and thank you very much for your support. As far as the practical organization is concerned, I just want to thank a few people in particular. From corporate communication and marketing, Amira Brown, Krista Davids, Chuma Takala, and Jonathan Dale Blankenberg. And then on the streaming, Justin Alberts. So thank you very much for all the work that went into making this event happen. It's really appreciated. And then it's very nice that we get to do this at STIAS, particularly because it's famous for the wonderful snacks and refreshments and that sort of thing. So after this, please do, those attending in person, please do stay and join us for refreshments. Thank you.